Director of Harish Chandra Research Institute, HRI, which is there in Allahabad. Now it is called Prayagraj. Okay, so that is the place you are there. After that, you have been in SL Bose Institute in Calcutta, and later he moved to Chennai. He's a Madrasi. So he has been here associated with Chennai Mathematical Institute, like me, who associated with the Institute of Mathematics. So we have been talking and discussing several things. So the HS Money works on high energy physics, and that is his expertise. So he has been of late following various issues in quantum mechanics, and he's a great teacher. The greatest thing about him is his teacher. As a teacher, he is regarded as a great teacher in IIT Kanpur, where he was worked a long time, and also in many other places. So that is Professor Roychowdhury. The next is Professor Sibasish Ghosh, who was my colleague in the Institute of Mathematical Sciences. He works on quantum information theory, or these issues about foundations of quantum mechanics to some extent. And he is a person who is actually working in many of these questions, theoretical works he has been doing, and he has been in touch with several other institutions outside as well. He is a well-regarded physicist who is, in my opinion, in Madras, there are only a few people who can talk about these kind of things in details, and he is one of them. So I'm very happy Sibasish has agreed to speak and was just to take initiative to talk about this. So I'm going to cut down my talk, and I will leave it to Professor HS Mani to introduce, following which Sibasish Ghosh will follow with what he is. Okay, thank you.
Thank you. Good evening to you all. Firstly, I would like to thank P.R. Govindarajan and his crew for doing such a wonderful program here. It is really remarkable that you people are doing. I think we have to appreciate that. Thank you. Now, regarding today's talk, I will just give you an introduction and get your appetite for the situation we are in terms of quantum mechanics. It is actually a very confused state of affairs as far as many ideas are concerned. It conflicts with us, with our normal way of thinking. The example I like to quote, and there are several. In the development of physics, when concept of something like force, it took more than 150-200 years to realize that what we teach physics of force in the high school. Similarly, the concept of heat, which we think of as a form of energy, it also took 2 decades. Now we are in a similar threshold in quantum mechanics, and this is the main aim we would like to emphasize. Do you agree? So, given that, I would just like to give you an introduction to somewhat to Professor Ghosh's presentation. So I will just start with this. The Nobel Prize was given to Alain Aspect and John Clauser and Ankel Seilinger. Quantum mechanics, as I have mentioned just now, our understanding of nature, just like the understanding of heat, changed when we understood it in the form of mechanical energy, or it is another form of energy. This change is taking place. The work of Alain Aspect and John Clauser has actually demonstrated this experimentally. Who will do this? நீங்களே பண்ணிடுறேன் நான் சொல்லிடுறேன்.
Okay.
Next. Now you could go to the next slide, please. Okay. Yeah, this is the kind of broad apparatus that was used by Clauser and Aspect. There in the middle, there is a source which emits 2 photons in 2 different directions, opposite direction. And the photons are characterized by what are called their polarization. They can have different kinds of polarization. They can be set up again from one polarization to another by using certain optical devices. And then you measure a correlation between the polarization of the photon to the left and correlation between photon to the right. They will, of course, carry the information when they left the source. But the way the information is categorized in classical physics is very different from quantum mechanics. This is the point which will be emphasized later by Professor Ghosh in great length. And when the experiments were performed, they led to certain relations, and they are put in terms of some inequality. Some number, if it is classical, must be less than 2. But experimentally, that is not true. That number, when actually experiments were carried out, was much greater than 2. This is what is called a violation of the Bell's inequality. Bell is the first person who established such inequality. Before that, people were just generally discussing things, but Bell brought it in the front of an experiment to show the classical thinking will not always match the quantum thinking. Next slide, sir. And this requires, as Professor Vwani has mentioned, the idea of entanglement. They use these entangled states. The source which I showed in the previous slide had those entangled states. Then Zeilinger used these entangled states also to do what Professor Vwani said, to teleport a state from one place to another. Here I would like to explain a little bit. It is classically also I can teleport a thing. It is I take a sheet of paper, I take it, put it in a photocopy, and I can send it to IMSC to picked up by somebody. So I'm teleporting it from you to there. And you give me another sheet of paper, I can do that. In quantum mechanics, you cannot do that. If I put one paper, the machine has to be specifically arranged for that copying to be done for that paper. And once that is done, that machine is useless as far as further copying is concerned. If I have to copy another paper, I have to hunt for another machine and then do this process. Very different from the classical solution. So this is something, yes, A will be able to teleport something to B, but what A had is gone. Now it has to be replaced by again another process to be replaced before we can do that. That's the difference. And now we will make an appropriate transformation to get the state. This leads to the development of quantum computation and quantum cryptography. This is the clues where a person, when he tries to disturb the system to look at it, this information would have reached the parties which are sending the thing, and how efficiently you should do. Okay. And the other side would like to say how efficiently he can see doesn't disturb the system are part of the game that's being played in the last 2 decades or 3 decades. Please, the next slide. It's working now. Yeah. So this one. Now I will give you a mind-boggling example of what is called the quantum pigeonhole principle. This is really mind-boggling. Supposing I have 2 holes and 3 pigeons living in 2 holes. Ordinary thinking would tell you that one of the holes must have 2 pigeons. Quantum mechanics, this is not true. I can make a measurement for 2 pigeons in hole 1, I will not find it. I can make a measurement for finding it hole 2, you will not find it. There are such states and such measurements, and those of you who are interested in understanding this more, I can give you the papers and help you work it out to understand how the basic ideas are. So you can see how different quantum mechanics is from classical mechanics. The quantum pigeonhole principle is just not there. Okay. Now, next thing, having told you how different it is, and we have to understand all this properly, we need some mathematical apparatus. And here, I will like to discuss a 2-dimensional vector space to understand the work of the Nobel Prize winners. I will talk, normally one would have talked in terms of bits takes 0 and 1. All bits in our computer will take 0 and 1. There are 2 states. Quantum bits have a much bigger space to operate. Instead of talking in terms of quantum bits, I'm going to talk in terms of something which undergraduate physics people know is in the form of light which is traveling. The polarization vectors. And anyway, the experiment done by Clausen and Zeilinger were using photons. Now, the wave, if I have a wave which is traveling, say, in this direction, the electric light is a form of electromagnetic wave. So I have electric field in a direction perpendicular to the motion of the wave, and magnetic field is in that direction. So electric field to magnetic field, if I do, it will move that way. At any given place, the electric field will vary like this. It has to keep varying. That variation is what produces the magnetic field, and they help each other in doing this. That's how the electromagnetic wave proceeds. So the wave is transverse. The electric field, supposing the electromagnetic wave is along the z direction, the electric field will be along the x in the xy plane. They are also mutually perpendicular. So E, B, and K, they form a right-handed coordinate system. E, B, and K form a right-handed coordinate system.
This one. The companion device is in the computer. Press it like this. This is entitled to that device.
No,
This one is entitled to that.
no, next page you wanted.
Yeah.
That was next. This is a way depicted an animation, and again I must thank Ritesh Bharat. Is he here today? He is the person who helped me with all this. He did all this from Pondicherry and did all that work. Yeah. Next slide, please. I have here a polarization. It can be, the polarization can be along x-axis or y-axis, which I have written as Ex times a unit vector along x-axis, and that is Exi gap, and another unit vector along y-axis. And I will assume here is where a little bit of mathematics comes. The oscillation which I write down is in terms of the following formula, which I have written to the right-hand side. Can I show that? Is there a light I can lay some beam?
Yeah, yes, please.
Yeah. This is enough. No, it's light you on laser.
No.
Yeah, give me.
No, you have.
Wait. Give me.
Pointing it to a computer.
No.
Oh, I have to do it this way?
No, wait. You don't point to
This,
Yeah, I thought that's right.
this one.
That's
this one.
I have gone forward. No. Here it is. This formula is the what I use, e to the minus I theta. Cosine theta is a sinusoid, it varies, oscillates like that, so does sine. So these are the equations which I have, which we learn actually in trigonometry in school. But if you're in biology or medicine, you might not remember it. But the main idea is that there is oscillation which takes place. Here is how it goes. This is one kind of possible polarization. These are called linear polarization. Here is another. You could also do it in a third way, which will be a combination of these two, and that's called a circular polarization. One could be left circularly polarized, another one right circularly polarized. This is the right circularly polarized which I'm showing here. And the details of how this happens are worked out here. I will not go over all the details. Those of you who are interested can always stop and find out. Next is here, I've redrawn this. Notice at any given point, the light, no, I've gone forward.
That's a.
There is a red
Here
button.
it is. Now notice it is going anti-clockwise and the beam is going forward. This is left circle. If it is clockwise, then it is right side. Now, these things can be written in terms of a column, what is called the matrix. Right circular, I write is Ex, Ey. Left, I write Exi. I is square root of -1. I can combine this and write Ex in terms of these two. These are the mathematical things which Professor Ghosh may need, and so I have written it in this Ex. Notice I can write down in terms of linear polarization as a combination of right, left, and right. Here it's a -I, here is a plus. So I can write down all these possibilities, and experimentally you can produce all of these possibilities. separate. Okay, here it is. Here is the linear polarization, and I have broken it up into two. One left circularly polarized, another one right circularly polarized. These two add up to this. Okay, the same thing has been redone and rewritten in the following form. Here is a vector in the x direction moving like that. Here is a vector which is, all these are about electric field of the light. And here, this is the right, which is clockwise, and this is anti-clockwise. And there are several other possibilities. I will just deal with these now. Others are very similar. Okay. There is another geometric interpretation of a two-level quantum system. These are for whatever the states we have been discussing, and they are called the pure states. The most general two-level system can be represented by an expression like this. There are two. This is just an overall phase, and I don't need that. I only use these two ones, and this is polar coordinates. Notice here, this is my x-axis, this is my y-axis, and that's my z-axis. And the polar coordinates which you use are the length is 1, and this angle right here, psi, is a quantum state. So psi here, it's the same state. And now here, this angle is phi, the azimuthal angle, which is here, which can go to 2 pi. Theta can go from 0 to pi. So now, if I take theta equal to 0, then I will just have a state right here that we want to. Every point on the surface of the sphere is a state. So I have 0. Let me go here. This corresponds to theta equal to pi. When I put theta equal to pi, cos pi by 2 is 0, sin pi by 2 is 1. So it is this state. Similarly, I can write down states here. These are circularly polarized. All the ones from the equator are circularly polarized. So in between, I can have many states, and this is a way in which a pure state can be represented on a screen. This is a geometrical representation of a quantum system. Now, next important concept, which I've already talked about at length quite a bit, is about the measurement in classical. In classical physics, measurement means a property exists predetermined, and it was observed by a measuring device. Example, take a temperature of a bottle. If I take this water bottle, I assume that its temperature is known. I have to only measure it. How would I measure it? I will insert a thermometer, and the heat capacity of the thermometer should be much less than the heat capacity of the water in the bottle, so that there is no change of the temperature of the water bottle. And if I make the heat capacity go to small, the temperature changes of the water bottle will be negligible. So I can measure the temperature of the water bottle without disturbing its temperature in the limits. In quantum mechanics, this is not necessarily so. Again, I could manage. Quantum mechanics, why is this there? Okay. Here it is. It need not have a predetermined value. It could be a combination, an outcome is obtained. The system gets disturbed and it comes to a new state, that state collapses. In general, it is not possible in quantum mechanics to make a measurement without disturbing the system. And this is what leads to the famous Heisenberg uncertainty principle and leads to here. Here are two things which are written. The position in space, if I am putting the moment, this is the wave function measurement, and if I make a measurement, the system will collapse to a state like that. But in general, it was a system of that nature. Now, the actual experiment which produced the two photons in the experiment at Clauser, I'm just giving you some details here. And there's the purpose I'm giving it, I will mention that. What happens is there's a laser beam which comes and it interacts with the crystal and produces two beams. And the two beams come out in the form of cones. One cone upper and one cone lower. And where they meet, where the cones meet here, the photons which are coming in there, photons are coming, 2 photons are coming with lower energy than the original beam. Original beam at say some 2 MeV, 2 electron volt. This could be 1 electron volt. And one of them will come in with on a cone, the other one will come here. That will depend upon the crystal structure of the crystal. We are not interested in those details, but they will meet. If they meet at the place where the photons are coming, they are entangled. These are entangled photons. This is how entangled photons are. And the kind of things that are required are these KDP crystals, that are called spontaneous parametric breakdown or spontaneous parametric down, right? Down conversion. Right. So now the point is, in India also, several such experiments should be done, and it was about say 10 years ago. I was also interested in seeing some undergraduate experiments can be done. American Journal of Physics, which is the place to look for, you see several such undergraduate experiments done all over United States and India. So why should we not be doing it? So I got into touch with persons who are doing experimental work in Raman Research Institute, IIT Kanpur, Anant Ramakrishnan. And Anant Ramakrishnan, being an old friend of mine, I could talk to him more, and he said these are all very expensive crystals. And detect all these are photons which have very little intensity. You can't use 10,000 photons. So you need 1 photon, and then you need detectors which can measure such low intensity. So this kind of work is very, very difficult and very challenging. But again, unless we do this kind of work, we will be left behind like what we have been always being left behind. So this is a challenge for all of us to see what are the kind of experiments we can go and do it in an undergraduate lab. Maybe some of them are not very easy. Quantum erasure is one possibility, and there are several such possibilities which will explain the basics of quantum. Instead of just going on measuring using Fourier thing about heat conduction and so on, which is about 200 years old, and we can just try to do it. That's one of the reasons why I put up this slide. And okay, using all this, there was an inequality established derived by these relations were in the form. I've already mentioned that. If they're a weight class. Aspect, Clauser, and co-workers experimentally found that 2 correlated photons, that these inequalities are not satisfied by a large lambda. The main assumption in deriving these inequalities, they are classically correlated. The exact mathematics of it is a little involved, but it's not all that difficult. It can be understood by an undergraduate student. This implies certain possibilities can be assigned to different choices of measurement. This forces us these inequalities. And here is the actual apparatus which is used. Light comes here, is your spontaneous down conversion. The 2 photons coming, and these are focusing the photons. These are halfway plate A and B, and these are beam splitters taking it to detectors, and they take to 4 different detectors. One on this side of the photon, the other side. And these are the correlations. And one should also ensure that there is no communication from here to here, and that again is a very interesting technical method of doing it by having these things work at very, very rapid frequencies so that the photon here cannot interact with the photon. This is the problem. And the measurement uses the entangled states all the time. And this is, of course, I mentioned again and again. Perhaps one can extract work from the measurements. And here, I must say, Professor Ghosh has a very nice paper on how using measurement, one can use it as a Carnot cycle and measure, get an energy output. And here is a famous Schrodinger cat, radioactive substance hitting liver, and the liver collapses, and some kind of a poison or whatever is emitted. The cat is living, and instead of the standard thing, I'm going to say it's sleeping. And so it is a mixture of states, which is a combined state of a living state and a awake state and a sleeping state. But these are the kind of questions which have to be answered. When it comes to macromolecules, how can you do this? I thank you, and I will now request Mr. Ghosh.
It's a very difficult task. Okay. I actually requested him to minimize the mathematics. And he did make definitely great effort. And there is some mathematics is needed. We cannot avoid it. But what was the mathematics used was only what is done in two-dimensional physics, right? X-axis, Y-axis, vectors like that. So it's going to be that kind of a thing. Now, Professor Ghosh will continue and try to tell you precisely what was done by Alan Aspect, John Clauser, and Zelinger, for whom the Nobel Prize has been given. Okay, now, Professor Ghosh.
Okay, thank you, Professor P.H.D. and thank you all to be here to attend this Nobel Prize 2022 physics lecture. I must thank Professor Roychowdhury to make my life much easier because otherwise, in the short span of time, it will be much difficult for me to explain all these things. Okay, so so this is so my topic. So the title of this talk is quantum entanglement. So the Nobel Prize has been given on entanglement and its experimental verification and research. So let me try to take you into a little bit of what entanglement means, what can I do with that, and what about the experimental verifications of entanglement and related issues. Before doing that, let me try to introduce this notion of indeterminism. Professor Vwani introduced this notion of indeterminism of measurement outcome in quantum mechanics. Let me try to introduce it once again to just compare the situation with the classical world. When I say classical world, it means the world where we live, our surroundings, where the laws of classical physics will hold good. Namely, Newtonian mechanics, classical thermodynamics, then classical optics, all these things will basically, it will hold. Okay. So the question is there indeterminism in measurement in classical world? One might say yes, why not?
Red button.
Red button. That's the.
No, he wants to change the way.
Change the way. Okay. Yeah, try now.
Okay. So let us go through this example of coin toss. Everybody here knows what coin toss means. Whenever we get to see cricket match, football match, etc., I mean, who will start batting, etc. That is decided by the result of coin toss. So if I do coin tossing,
No, it is.
Yeah.
Next.
Yeah.
So this coin tossing, you say that when I toss a coin, I'll have either head or tail. When I get to see what result is coming out, it will be either head or tail. Question is, can I say applied before doing this coin tossing experiment, what will be the outcome, head or tail? If I can do that, then that will be the idea of determinism. So I can do it deterministically. Okay. So the answer in the classical world is yes. We can actually tell what will be the outcome of a coin tossing, provided we know what force we have applied, what velocity or speed was the initial velocity or speed of the coin, what was the reaction or interaction of the coin with the air, that means air resistance, what was the reaction when it falls on the ground. If we know all these issues, then we can figure out without doing this coin tossing experiment, what will be the outcome, exactly the outcome. So in other words, in classical world, there is no indeterminism in principle. Even though, there are events where we don't know what is going to happen. For example, whether I'll be alive next 1 month or so, I cannot tell. Okay, so these kind of issues are there. But in every physical phenomena, what we get to see around us is deterministic in principle. It is our subjective intolerance that we can't tell a priori what will be the outcome. Okay. So in classical world, there is in principle no indeterminate. Everything is determined. Okay. So that is our point of. Now one might say, okay, how do I know that if I am or some material here is correlated with something else, some event is correlated with something else which is far apart, and if I do some measurement on my system, how this correlation is going to be affected, and on the other hand, how this correlation is going to affect my measurement. Like, if I work on flow, unless there is a friction, I will fall account to justify why I am not falling every time. So that's a kind of correlation. When I look at prices of goods in market, like whatever we take for our food, etc., like lentils or paddy, whatever, then we have to see what is the price of the petrol or diesel, because that price will be increasing the price in petrol or diesel will also affect the price of goods. So there is this kind of correlations are there. Okay. So the question is that if there is material correlation, like I have two walls, material walls, which are connected with a spring, and let us keep it on this table. So if I move one wall, the other wall will also move. If I move it fast, the other wall will also move fast. Okay? So there is a material connection. So you can say these two walls are connected, correlated. They are correlated. On the other hand, we can have correlations without such a material connection, like yields in paddy. Okay? That will depend upon the rainfall in a region. So there is no direct material connection, but the correlation is there. Connection is there. So if there is huge amount of rainfall, there may be, it is going to affect the amount of yields in the paddy. Okay. So these are kind of correlations we are associated with our day-to-day life. Okay. So the question is, when things are correlated, two things or more than two things are correlated, and when I want to look at certain property of one particular thing, one subset of that, I mean, it is still true that the event, let's say I take these two masses associated with this thing. If I move this mass, of course this mass will also move. But the question is that, can I say that the movement of this mass is completely deterministic? Okay, in the sense that even if there is some correlation, still it is deterministic. So in everyday life, we have some deterministic event, like sun will rise on the east every day. There is no change. But there are also issues which are probabilistic in nature, statistical in nature. And it is these events which are statistical in nature that create some problem in justifying whether the event associated with the statistical nature is deterministic or not. Okay. So here also, as I said, that in the case of one mass, two masses connected with this string, even movement of one mass is determined. One can make it determined. It's not a problem by knowing everything. Similarly, in the case of, let's say, second mass also it is. So it means that when I talk about correlation, one might say that, look, I have two masses, they are connected in string. I move this mass, the other mass will also move. If I move it faster, it will also move faster. If I pull it there faster, it will go on this side. Okay, so this kind of correlation is there. Question is that, can I, when they are correlated, or when they are not correlated, can I determine the displacement of this mass or the speed of this mass together at a time? Like, you have a moving car. Can I figure out what is the speed of this car at a time, and as well as how much it has moved. That will be different. Can I do it simultaneously? Yes. In classical world, we can do. There is no harm in it, even if it is coordinated. Right. So we'll see that all these notions, this determinism, and the simultaneous hard values of measurable quantities are not the case in quantum. Okay. So, two notions which are very, very fundamental in order to understand why Nobel Prize has been given this year on these entanglement and related issues. So these two notions are very, very important. One is the idea of locality. So, locality is that, let's say I talk about again these two masses, two balls connected with string. If I move this mass here, I know this will move, but it is not instantaneous. So it will take some time for the second mass to have movement. Okay. For example, I take a magnet, a bar magnet or whatsoever on this table and put some, iron here, iron body, maybe some nails. If I bring the magnet towards this iron, these nails will be, attractive, but it will take time. However small it will take time. So, what I want to say is that this influence, that I'm disturbing it, moving it, etc., this influence in classical world cannot, happen instantly. It takes. And what we know from physics background that no information, physical information, can have speed much, greater than the speed of light. So there is a finite speed of any information that can, any influence that can. This is true in classical world. It should be true in quantum also. Right. So the locality principle tells you that when I do something here on my system, the outcome of this doing something, that is outcome of this observation or measurement, is not going to have influence the other system instantaneously. Okay, so that is the notion of locality. And all of us agree that yes, our classical world should have this property. The other one is this notion of determinism, which I introduced, initially, that in classical world, every event is in principle deterministic. Okay? And so it tells you that the result of each measurement or observation process can be predicted with certainty in principle. I have come with this subjective ignorance that I told you. That means I don't know the force, etc. Therefore, I can't tell you, beforehand. If I know all this, I can tell you. So, the important thing which Professor Vwani alluded to is that whenever I perform measurement, what is the speed of this vehicle, what is the length of this table, etc., it will reveal the measurement. If I do it properly, it will reveal only those values. Like if this table is, let's say, 1 meter length, it cannot reveal, if I do it properly, the measurement, it cannot tell you that its length is half meter. Okay, it cannot tell you. So, proper measurement, if I do it intelligently and properly, will only reveal the values of those observable quantities, nothing else. Okay. So, its locality and determinism are the two basic ingredients of whatever physical world we get. Around us. Classical physics, whatever we get to see, these two notions, reality and locality, or reality is also called as determinism. So determinism and locality are two basic principles of the classical physics that you are aware of. You can forget about any other property of classical physics, okay, for our discussion. Just these two principles we'll talk about. Okay, good. The next notion, now, okay, so people going into that. So it was Albert Einstein. Albert Einstein got, he did works in physics, which changed our world. There is no doubt. Before Einstein, the world we used to perceive is one. After Einstein's work, it is something else. Okay. But Einstein was a strong proponent of determinism in our world. So he used to say that, look, God doesn't play dice. Okay? So whatever happens in our world, classical world around us, it should be deterministic in place. If I cannot tell you, he will tell you. If I and you cannot tell you, somebody else can tell you. Okay? The outcome of measurement deterministic. And it is this notion of Einstein which he carried out throughout his entire life. Okay? So now, point is that in science, I cannot just say that I am a believer in determinism or I am not a believer in determinism. If I say that, it doesn't make much sense. So it should be contextual. Okay. So what Einstein did to make our life, like the physicists working in the later years, difficult, is that he wanted to convince that, look, quantum theory that we people are talking about is correct because it can provide results which are incommensurate, which are commensurate with or compatible with the experimental result, no doubt of it, but it is incomplete. So what is the notion of completeness that Einstein means? So according to Einstein, a complete physical theory, that means theory of nature, maybe classical physics, quantum physics, whatsoever, or some other candidate, it must possess the allowed values of all its observable quantities, be position, momentum, energy, etc., etc. Okay. And whenever I perform measurement, it must reveal only these values and nothing else. And it doesn't matter which observable quantities or how many observable quantities I am going to measure together. It doesn't matter. So that was the notion of completeness which Einstein used. Okay. So as I said, if I have a moving car, I can figure out its speed, how much distance is caused, what is the mechanical energy, everything I can figure out in hospital. So the question is that Einstein, when quantum theory disturbed him so much that for a single quantum system, let me say maybe an electron, maybe a photon or whatsoever, so he wanted to tell that, look, when I perform measurement on a single quantum system, like if I have a photon, I want to measure what is its polarization. Is it horizontally polarized or vertically polarized? Whenever I have a spin, I want to figure out whether the spin is along positive z direction or negative z direction, etc. Quantum mechanics tells you that no, you cannot tell with certainty. There will be some probability of getting up z spin or down z spin. There will be some probability of getting horizontal polarization or vertical polarization. So that is what I mentioned initially, that this indeterminism is kind of inherent in quantum, which Einstein was completely against. So what he did is, so for a single system, to say that, look, there must be some underlying theory, our subjective intolerance is there, therefore I cannot predict with certainty what will be the measurement outcome in quantum world. The point is we cannot, neither we can contradict you, nor we can support, unless we specify further properties. So what Einstein did is that he introduced a bipartite system, or Professor Vwani told a system of two photons polarization, or a system of two spinors together. And that using that he wanted to, he wanted to prove that quantum theory is incomplete. Okay, so So existence of this incompatible set of observables of any single quantum system does not allow to have sharp values. Sharp values means, so what is, I said, exact length of the table or whatever. As measurement of one observable, so as Prof Vwani said, in quantum theory, in quantum world, if I perform measurement of some observable quantity, like position or momentum or whatsoever, or spin, it is going to disturb the state of the system. Therefore, if I want to measure some other observable, I will not get the exact value. Unlike in classical world, I can in principle perform measurement without disturbing the state. So I can measure the speed of a moving car without disturbing its motion. In principle, I can do that. Okay. So what Einstein did is using a coordinated state of a composite quantum system consisting of two subsystems and inferring the sharp values of simultaneous measurements of two incompatible objects. So what we did is we took these two systems, we did something on this system, but the other system is far apart. So as I said, whatever I am doing on this system is not going to disturb the other system instantaneously. Therefore, if I can infer values of observable quantities of this system, we need something here. Okay, then quantum mechanics you will see tells you that we cannot do that. We cannot have sharp values of right. So Einstein's argument, I'm not going into the details of Einstein's argument. Basically, I'm trying to give you the rough picture. So what Einstein did is doing something on this system, and these two systems A and B. If A and B are correlated, doing something here is going to affect the measurement outcome of the B system instantaneously. And if I do two such measurements on A system, I can figure out the values of measured values of some measurable quantities of this other system. And quantum theory tells you that in general, observable quantities are incompatible. You cannot do joint measurements, simultaneous measurement of those quantities. Unlike in the case of a moving car, where you can figure out the speed as well as displacement of these things. Right. So the question is then, what about quantum theory? Is it incomplete according to Einstein, or is there something else? So as I said in the beginning, we are not in a position to tell you whether quantum mechanics is incomplete or not, unless we specify some further properties. What we can tell you, and that is what John Bell showed, and later these people who got the Nobel Prize this year, they showed experimentally that this idea of locality and realism or determinism together, which is called as local realism, is incompatible with quantum mechanics. So, quantum mechanical measurements on these two systems separately, the measurement statistics that it will provide you, will have inconsistencies with this principle of local realism, locality and determinism. So this is what we are sure of. Okay. So actually, now it was 1935 then when Einstein, Podolsky, and Rosen gave this argument that quantum theory is incomplete. 30 years, about 30 years were spent where people were discussing metaphysically, philosophically, etc. But no outcome, no definite outcome came out, which can tell you that, look, I have this formula, I have this procedure. You go in lab and test whether quantum mechanics is incomplete or not. Test whether quantum mechanics is incompatible with local realism. So it was John Stuart Bell, was a particle physicist in CERN, who actually came up with this this idea of statistical inequality, which we call as Bell's inequality, which Professor Vwani has told you earlier. And this Bell's inequality, if one can go to a lab and do measurements on entangled system and figure out whether this inequality is violated or satisfied. If it is violated, then we are sure that quantum theory is incompatible with the notion of local realism. So there is indeterminism in quantum theory. But this indeterminism cannot be explained by the notion of local relativism. Okay, good. So to make things shorter, so after this, so John Bell gave this, this Bell's inequality in 1964, although the paper was published slightly later. This is an obscure journal, it's called Physics, volume 1 it was published. After John Bell, this is 64, people started. Now, John Bell gave this Bell's inequality, looking into measurement correlation of a specific state, which he called as singlet state. I'll come to that. Later on, in 1969, Clauser, Horne, Shimoni, and Holt, they came up with a more general inequality, statistical inequality, which does not, take into account only the correlations in single state, any state of these two photons, polarization. And nowadays, we call such inequality as Bell CHSH inequality. And this inequality, Bell CHSH inequality, has a broader perspective from the experimentalist point of view. Because, in experiment, you cannot figure out that everything is very sharp, everything is very correct. There will be errors. So this inequality can take into account all those things. So, so the inequality that we will talk about is this Bell CHSH inequality. Now, thereafter, in 1972, the first experimental violation of the Bell CHSH inequality was done by Friedman and Clauser. Friedman was the PhD student of Clauser. And every such Bell experiment, the important thing is producing this entangled state of, in this case, two photons. Okay. Now there was, of course, it was very challenging, as Prof Vwani mentioned, because we have just two photons. Think of it, the light, this light has plenty of photons, billions. And if you want to have a photo detector which can detect a single photon at a time, it's much bigger. But we are developing. We are at a stage where we can have detector which can detect a single photon with a very high accuracy. Right, even more than 90%. Okay. But at that time, 1972, things were not too easy technically. Okay. So then it was Alan Aspect and his collaborators who in 1980, actually they started from 1981, they started doing series of experiments for testing violation of Bell inequality with these two photon polarized states. And they developed much sophisticated experiment and which can take into account some loopholes. I'll talk about these loopholes. It's called locality loopholes. So these Alan Aspect's experiment was, to take into account this locality loophole. Then Anton Zeilinger and his collaborators, what they did, Zeilinger is somebody, if you go to his homepage, you will see that all sorts of experimental quantum foundations and information, which is possible or will be possible using photons that we can manage. However difficult. Okay. So, the Zeilinger and his collaborators, they use these entangled photons for what is known as quantum teleportation for experimental, verification of. So the first experimental verification of quantum teleportation, that means sending information of quantum mechanical states of quantum mechanical system from one place to another place, arbitrary state of quantum mechanical system, and that was done experimentally verified first by Zeilinger. Later on, Zeilinger also did this Bell inequality violation experiment. In fact, the latest one in 2018, what he and his collaborators have done is excellent. He talks about all loophole free basically. All these loopholes what we will talk about, he came up with experiment which can get rid of all this. And this is much sophisticated. Okay, so what I do, I'll not go through all these details.
Okay.
Okay. So now, in order to make you understand some of these issues, Professor Vwani has already told, but I'll have to introduce little bit, not much, little bit about basics of quantum theory. We don't generally talk about basics of classical physics. You're all familiar. Even if you don't know the laws exactly, you're all familiar. Newton, yes. So, so if I think of a coin tossing, the coin has head or tail, these two faces. Nobody can tell that, well, it can be something in between, half head, half tail, can you have a coin like that? Unfortunately. Okay. Like a cat can be alive or dead. Can there be a state of cat which is in between? Okay. So, in quantum theory, this is not the case. In quantum theory, you can have like polarization of light of a photon, horizontal polarization of a photon, and vertical polarization of a photon. Vertical polarization of a photon, which are orthogonal, which are perpendicular, which are distinguishable perfectly, but you can also have something in between. That means polarization along 45, polarization along 135, linearly polarized, circularly polarized, superpositions. All these are possible in quantum. Okay. So when I say in quantum theory, in classical world, any two states, like whether it's head or tail, whether the car is moving or it is static, every such thing are distinguishable. In quantum world, this is not the case. So, unfortunately, I have to use this Dirac notation, but forget about it. Just think of it just a vector, as Professor Vwani introduced. So, I can have horizontally polarized photon or vertically polarized photon, which are perfectly distinguishable, or you can have also linear superposition of these two. This is a normalized, so the coefficient mod square. So this is a state of a photon polarization, which is linear superposition of horizontal and vertical. If you measure what is the polarization theta by 2 horizontal, with probability sin square theta by 2 equals 5. Unlike in the classical. In classical world, if I toss a coin, after looking at the outcome, I'd say definitely it is head. I'd say definitely it is head. Nothing in between. Okay, good. So polarized light, I will not go through this thing. So basically, people use how to polarize a light. So this light, what is coming from here or from the, so these are not polarized. Not polarized means it has infinitely many polarization, a mixture of all these things. Okay, but so polarization means the electric field and the magnetic field in a particular direction. Okay. So when light passes to something called Polaroid, a kind of crystal, it have a definite direction, which is this polarization direction. So you can basically prepare polarized light. If it is a like horizontal polarized, you can prepare a vertically polarized light or some other polarized light by something what is known as wavelengths, quarter wavelengths, half wavelengths, or combination of that. Good. And when we talk about the composite system, like a two photon or two spins, their states, like if we have two coins, if I toss them independently, I'll have head, tail, or tail, and all of them are distinct. In the case of two photon polarization, I can have all these states, HH, HV, VH, VU, but also their and this state is not distinguishable from A, isn't that? Okay, good. So this is all about the states, that photon polarization, how to prepare. There are different ways. You can use a particular polarized light and then use this quarter wave plate, half wave plate, prepare another polarized. For two photon polarized entangled state, so the first experiment was done when you take some calcium atom and then heat it up to a particular level so that it will release some photon. It will come to, so this is an excited state, it's total angular momentum 0. It will come to a lower energy level state with total angular momentum 1, and then again it will release photon to come down at the ground state with total angular momentum j equal to 0. So these two processes, so release of a photon V1 and release of a photon V2 can happen almost simultaneously, and they are kind of correlated. And this is how you can prepare a two-photon polarized correlated state. And this is what is known as preparing two-photon polarized state using atomic cascade. This is the cascade. And this is the process which Clauser and his student used, as well as Alan Aspect and his collaborator used for testing Hallett compensation. More modern version is what Prof Vwani said is the spontaneous parametric down conversion. So we have a laser light which we call pump light, like this light. Here is a crystal which we call nonlinear crystal, nonlinear in the sense that it will change the polarization of light nonlinearly, not linearly. Okay. And then what happens is occasionally, this is very, very rare phenomenon, that you will have two such beams with particular, these beams with particular, wave vector, this is particular wave vector. So that the sum of this wave vector is same as the wave vector of the input light, and energy, sum of energies of the wave vector is same as the energy of the input light. So this conservation is there. And then this is called signal light, this is called idle light, such that this is correlated in the sense that to put a photodetector, get a photon here, you will get a photon here. If you get two photons here, you will get two photons. And this situation is such that getting a single photon here and a single photon here is most probabilistic compared to others. Although this result can happen very, very rarely. But this is a process of preparing this two photon entangled state, polarized entangled state. And that is what people use these days for several experiments, not just for valuing. Okay, maybe I'll not go through this presentation, you will find. I'll go through this. And observables, as I said, we can measure condition, measure momentum, and measure polarization. So one rule tells you that if I measure, because quantum mechanical measurement is important, if I measure an observable A, which will position momentum, spinning polarization, etc., and prepare this system in which it gets vector charge, it will provide one of the outcomes, and if one of the outcomes are eigenvalues of this observable. So this is slightly mathematical. This observable means it's a matrix which is Hermitian. If you take dagger or adjoint, it will be the same as this. So its eigenvalues are real, and eigenvectors are also orthogonal. So the ith eigenvalue will occur with this probability. So this is the overlap of these two vectors, psi and psi, or square. And after the measurement, the system will jump or collapse into these corresponding eigenstate values. So this is what we understand by quantum. Unlike in classical world, this collapse happens. And there is a big problem, which is called measurement problem, is how these collapse happen. Okay, so measurement of single system, as I said, this is the probability, and measurement on the combined system or entangled system, this is the entangled state, which is called similar state. So this is HB minus BH. H is the product. So when the A photon or when A photon is vertically polarized, B photon is horizontally polarized. This is the superposition of this. Okay, so if I measure. If I measure on the A photon, whether it is horizontally polarized or vertically polarized, if I get to see it is horizontally polarized, then the state, joint state of A and B photons is HB. If I get to see B, the A photon in B state, then the joint state of A and B Okay. So, and this is happening with probability half because not square of this way. And we say that this state psi minus is entangled because it cannot be written in this form. In the sense that I cannot assign a state vector to a photon and a state vector to a photon when this is entangled. Right. And well, I'll see that to basically how to measure these. That is fine. And another way, I mean, mathematically same is what is known as Tangala. So if you have electron which are spin, if you send like an atom, like silver atom, to this magnet, where north pole is there, south pole is there, and this is the magnetic field, homogeneous magnetic field along this direction. Then, unlike in the classical case, classically you will get the detection of the the atoms everywhere. I mean, some distribution, but in the quantum case, we will have this spot and this spot on the detector. So that makes the difference in the classical and quantum. Okay. So I have already given this argument of Einstein, Podolsky, and Rosen. I will not go through that. What basic thing is that Einstein said that look, by doing something, I mean, two measurements on my system here, I can figure out the values of two observable quantities on the other system without actually disturbing the others. And quantum theory tells you that such observable, like spin measurement along z direction and spin measurement along y direction, these are non-commutative. You cannot measure them jointly, simultaneously. You cannot have sharp values of spin along x direction and along y direction. Therefore, these the complete theory would have all that, but get the situation where on the B system I cannot. Therefore, quantum theory must be. Right. So I'll see this thing. So Bell's inequality, as I said, is so what John Bell did is that look, I will just stick to this local reality principle, local realism principle, and see what a physical theory tells us. What kind of inequality, statistical inequality we can provide. So for that, what he did is, so he used something called local hidden realism. So this local realism is that if I do something there, it is not going to affect the other system continuously. And if I perform measurement on my system, it will only reveal to values, nothing else. So using this local hidden variable means that these two systems, A and B, let's say two photons, polarization, they have an underlying connection, which may not be material connection. They have an underlying connection, which I call as lambda, so that based on the values of lambda, I can determine with certainty what is the measurement outcome of some observable for A system, what will be the measurement outcome of some observable for B system. Okay? So that is the idea of local hidden variable. So it says that this hidden variable can have hidden like when point of I don't know the force, I don't know the speed, initial speed, I don't know the air resistance. So if you put them together, I cannot figure out what exactly value of this variable is. Okay. So what Bell did is that using this notion of local hidden variable, he came up with this correlation. So the value of some observable BA can be plus or minus, BB can be plus or minus. It depends upon the observable A and this hidden variable. And then the hidden variable itself can be probabilistic. It can have probabilistic values. And then you take the average, which is here integration, which is the experimental joint correlation. And Bell inequality tells you that if on A side, if I perform measurement of this Kali A or Kali A prime, and on B side, if I perform measurement of Kali B and Kali B prime or Kali B prime, then this inequality, magnitude of this thing, CAB plus CAB prime plus CA prime B minus CA prime B prime, magnitude of this must be less than the two in a local hidden variable model. Okay, so this is what is known as Bell's inequality. Bell's inequality, Bell's original version is not exactly this, but as I said, this is okay. And then what Bell did is that for the single state, what I mentioned to you, this 1 by root 2 HB minus VH, if you take that and if you perform measurement of some observable like A prime, and these are basically observable in sigma dot J. So sigma X, sigma Y, sigma Z, these are the component for sigma vector, and J is the unit vector in 3 dimensions. Well, what we showed is that these quantities is correlation. QM means quantum mechanics. These can have value, maximum value to be, which is of course greater than 2. Therefore, we have a violation of Bell's implicity inequality in quantum. So now, is it the end of the story? One story is given. What is that story? It tells you that quantum theory has contradiction with local theory. So whether quantum theory, Einstein was happy with quantum theory or not, from the perspective of local realism, finished, got it. So what is it that we'll have to figure out? We'll have to figure out, well, one might say that who cares whether quantum theory is incompatible with local realism or not? Who said that quantum theory is proper description of nature? So we'll have to figure out from experiment that whether nature satisfies this local realism, whether correlations in nature, in experiment, measurements in experiment we do, whether that is compatible or incompatible with quantum. That is what we have to do. So the experiment is for justifying local realism in nature, not for quantum theory. Quantum theory, it has been established. Right. Okay. So this is the the directions of measurement. I will see this. So let me just mention briefly, because I'm not an experimentalist, we don't have time also, that what sort of experiment we have done for this taking of Bell design. So idea is that you have this source A which produces these entangled photons. For example, one photon goes to this polarizer, where we measure the polarization. Another photon goes to the left side for doing measurement of polarization. You can do polarization measurement along some direction, and you have two outcomes, whether it is polarized, vertically polarized or negative, or there is 145 degree polarized or 135 degree polarized. Similarly here. So you can have this X, Y, Z to X is this, Z is this, and perpendicular to this plane is Y axis. This is the general scheme. So the first experiment by Friedman and Clauser, they use this atom calcium oven to which basically oven atoms, and then have a laser light, party light is thrown on this atomic beam, and then for excitation it will produce these two photon states. One photon will go to this polarizer and then measurement, another photon will go to this and then measurement. Okay, and then we have a coincidence now. Coincidence see whether two photons are together or not. Now, this gave rise to violation of Bell inequality, but it is, beyond it. Oh, it is beyond any doubt. It is not beyond any doubt. There are too many loops. Okay, so as I said, drawbacks of this experiment: parts of the two output photons from atomic cascade do not have specific. So these are not specific parts. We have said this thing, but basically this is very broad. Here also very broad. So even if you put detectors like here, it doesn't matter. We cannot count everything. Photomultipliers, that means these photo detectors, these are not good detectors. And third, which is very important, is that we will have to justify that once the paired photons is created here, only after that you are performing. If you do the measurement beforehand, then it is something else. So this is what is known as locality loop. So this experiment is, it cannot void the locality. Okay. So if you want to, if you are slightly familiar with this special field, then you will see that this is the position and this is the time axis. So if you have entangled photon which is created in the past, and the measurement that you are performing on analysis side and work side, this event should come beforehand, before the light on, so that this creation of this photon, the paired photon, will not affect the choice of it. But outcome can happen. So this is basically the idea that was used by Alain Aspect, And he used the same thing, the atomic cascade, but they modified things so that they used some laser beam to create these photons, entangled photons, and then these coincident sound. But the distance between these two detectors from the source that invariably satisfies the locality. That means this locality loophole in these experiments is not. So the distance is, I think, is 10 meters or so. But then the problem is the detection. Photo detectors are very bad. At that time, you have maybe 20%, 30% efficiency. And whenever you have all these problems, okay. So then, good source, which is called spontaneous parametric down conversion came. And then in spontaneous parametric down conversion, the problem is, the thing is that, even though it is a rare phenomenon, still we know that whenever two photons are created, they have definite paths. So we don't have any problem. Okay. And people have used that also, like Mandel and his work was used for building. Now the question of loophole. So what happened is that there is this locality loophole I mentioned. There is also detection loophole. That means your detectors are not perfect. Question is, can we design a variable evaluation experiment which can take care of both these locality loopholes and detection, so that you will not have any of these. Experiment is done in photons. Photons don't interact. So it can pass through a large distance, but detection is very bad. Okay. On the other hand, if you take matter system like electron spin, etc., it cannot take a larger distance without affecting the system. But the detectors are very good. So you have to do something in between. And that is what in a group did with Roland Hansen in Delft University. What they did is what is known as entanglement swapping, where they use these two LV centers, nitrogen vacancy bond diamonds, and there the electrons are they have correlation with photons. I perform measurement on these two photons so that these electron spins they become entangled, and then you can do the values. The other experiment was done by Anton Zeilinger's group in Austria and this NIST Boulder group. So all these three have been done in 2015 to get rid of both these, these loopholes, and recently in 2018, Zeilinger and his collaborators. So locality loophole, detection loophole, done. We can say that these loopholes are not. There is one more loophole which is more philosophical in nature. What does it say? There are two systems, Alice and Bob. Two spins in two labs. I have to choose measurement, one of the two measurements on my system, one of the two measurements on his system, and he will choose. Question is, this choice should be, well in the experiment, this choice should be random. How do you decide that they have chosen it random? Number one. Number two, how will you decide that choice of one measurement and choice of other measurement, they did not have in common paths. They don't have any common paths. So how do you do that? So what people in physics generally take it to be, we take it to be granted is that what is called free will. So what measurement I will do on my system, it depends entirely on me, not on the car acquired. So this free will is it's a kind of philosophical issue, but what Weininger and his collaborators did is that the choice of measurement on one lab, he connected it with a cosmological event which happened, let's say, at the time of Big Bang, so that there won't be any connection. And there also we figured out violation of Big Bang. So now we are in a position to say that yes, we have actually full proof of well-integrated evaluation. So nature also does not satisfy in general this idea of locality. Now you might say that, what is the big deal? Let them behave like this. Well, the thing is that this as consequences. What are the consequences? Is that the security of quantum field distribution, the perfect randomness or certification of randomness of events, or certifying some measuring quantities using this quantum technology. It is based upon the Bell-Nickel difference. So once you can certify Bell-Nickel difference, you can certify several things. And those are all the technological aspects which people are working on, and hopefully in near future we'll get to see those technologies.
Let me actually context. Now, it cannot be done in 1 hour. What she has given is the introductory part. Now, basic question is nature, the laws of nature, deterministic or not? Now, we all know, and we have been using determinism, because we know sun rises every day morning, right? You can predict when it will come in the sky. We know when the eclipse will take place. That is determinism. In fact, we know for the next 1,000 years when the eclipse will take place, which place it will take place. Also, we know it to a very large extent. Okay? So there is determinism as given by Newton's law. The basis is what was given by Newton 400 years. Now, is the determinism or laws of motion as given by Newton, is it valid at atomic and lower scales which are there? That is the fundamental question. It raises extraordinary situations, and we had to revise, change. Now, as he mentioned, Einstein, being a believer in determinism, he said, yes, there is probability because of our inaccuracies in measurement, etc., etc. But the underlying theory is deterministic. That is the point. But when we do the measurements, quantum theory as given by Schrödinger, Heisenberg, etc., proved to be extremely successful. It is successful because you can measure the spectrum, hydrogen spectrum. We know even what is happening inside the sun. From the even stars, because from the spectrum itself, we know what is the temperature, what are the materials inside, what gas is there. All those things we know. Okay? But so quantum theory plays a role in precisely telling you what is happening. Now, the question which Einstein asked was, is it still, because the interpretation is probabilistic, is the underlying theory probabilistic or is it deterministic? That is the question which was bothering me. So, in order to circumvent all these things, they created something called hidden variables. Essentially, okay, these are the things, but there is something more than which we don't know. Since we don't know what are those things, we will average out. Whatever unknown variable is there, we will assume probability for that. As he said, I can in principle find out if I toss a coin, if I know the initial velocity, if I know all those things precisely, exactly, I can tell you classically whether you will get head or tail. Okay? But we don't know. So all those unknown information, put some variable and then call it hidden variable theory, etc. So quantum mechanics, quantum theory, can it be explained? The indeterminism which you find agreeing with Schrödinger's equation, etc., can it be explained by this kind of a mechanism? And what was Bell and others proved was that kind of hidden variable theory is incompatible with local things. That is all the basic things. And now the Bell's inequalities are very high. And it leads to certain new things, not only at the fundamental level of theory, in terms of applications. The quantum technologies, can I communicate? Can I give information, etc. So the earlier questions where all of us are dependent on money transactions through internet, etc. We will always wonder can I somebody hack in between? Well, can somebody collect that information and collect my data and take all my money out? That is the point. So the current system within the classical computer is that it is difficult, impossible. It is practically impossible to hack, because they have created a cryptography, some kind of a codes, which will be very difficult to do that. Okay, that is what the basic idea. Now, with the quantum thing, we can do that. There are more problems with that also. So there are a lot of interesting things in the last couple of decades, which has gone from speculative, philosophical, and other things to actual experimentation and technically finding out the results. So this is the status as of now. Now, as many college students have come, I would argue several people science forum know from IIT Madras, from our place, etc., who are reasonably well versed in what is happening in the aspects, well, Allen aspects work, and also what is the basis on which the Nobel Prizes have been given. So if you want any help in organizing in your own college, okay, program, if you contact us, we will provide appropriate links so that you can have little more discussion, more focused discussion, better understanding in your own places of institutions, so that other students, everyone will be benefited. So I'm going to stop it here.
Question answer.
So now we are going to start. We have in fact quite a bit of time. So we are going to start question and answer session. So all of you, there are a lot of you who would like to ask. Okay. So you should ask. Don't hesitate to ask. We'll go for at least half an hour to 45 minutes.
The first question we'll call from the internet.
Okay.
Meeting question.
It's from YouTube.
Okay.
May I know what is the entangled state?
Can you read it?
Yeah, may I know what is the entangled state, sir?
Okay, go ahead.
So as I said, entangled states are states of a composite quantum mechanical system, like a system of two photons polarized in a K polarization between, and it is a state such that we cannot assign a state vector to individual photon polarization. So that is what is known as entangled.
One more question from Zoom participant. Is the beta or kind of a decay from a nucleus is just because of presence of loophole in nucleus?
Beta decay.
Question?
Is the beta or any kind of decay from a nucleus is the just because of presence of loophole in nucleus?
Just because. No, it has nothing to do with that. So this alpha decay or beta decay in nucleus is due to a probability behavior of quantum theory, though it does not have that energy. Okay, there is a decay which is taking place and nothing to do with the issues about loophole system.
Okay.
The probability of the quantum theory, which is always like that.
Anyone want to raise any question? Please raise your hand.
Please raise your hand and then we'll go ahead and ask. Okay, here. Please identify yourself.
Sir, you can sit there.
Yeah. In the quantum cryptography, we will set the algorithm for the strings of clockwise or anti-clockwise using the binaries. We will transfer the data for the quantum using the cryptography. Okay. What is the base? My question is, can you set the algorithm for the quantum cryptography using the binaries?
Well, quantum cryptography, I'm not sure how familiar are you. So there are different ways of design. So cryptography, is basically sending information in a secure manner. Okay, and the scheme that people use in quantum cryptography is called one-time pair. So you have your message, which you can express in terms of binary string as in the computer class. Okay? You have a binary string that means 0, 1, 0, 1, 1, 0, etc., etc. And then you add another binary string, which is fixed, which is with me as well as with you. If I am the sender, you are the receiver. I add them, with binary. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, something like that. Binary. And then the resulting bit string, I'll send it to you. What you will do, you will add your same bit string, which is key, you will get the same bit. This is what is known as one-time pair. So in classical world, the sharing this key, which is called private key, is a difficult matter because any intercept can figure out in principle what is the shared key. Whatever the intelligent way by which you are sharing. In quantum world, sharing this key happens using fundamental laws of quantum mechanics, which tells you that two non-orthogonal states cannot be distinguished exactly. Or in other words, you cannot clone, make 2 copies or 3 copies of arbitrary quantum mechanics. So if you take like photon polarization, horizontal, vertical, 45 degree, 135 degree, send any such polarized photon to the receiver. Receiver can perform measurement in horizontal, vertical, or 45 degree, 130 degree to figure out the way it has been which basis it was prepared, and accordingly they will share the. This is the way it is done. And here, this question of eavesdropper getting hold of the message.
Thank you, sir. I just want to mention, see, in classical this thing, supposing your name is Raj, okay, RH. Now you want to send that information to that person to another person. Now, obviously, if you say somebody, some person can catch hold of that Raj and do whatever. So in order to do that, you say no, that is not RHA. For every letter R, I will put 3 letters from there. Instead of R, okay, A, B, C, D, O, K, P, Q, R, S, T, U. Okay, you put those 3 letters, every 3 letters. So that is a crypt which adopt, code which we adopt, or crypt which you use. And that is what is done. From there, the person who is in between part, he will get something like U, A, U, C, yeah, something like that you'll get. Oh, who is this? I don't even know who that name is. Unless he knows the clip, from there I have to go back and get that. Okay, so that is that class. The important thing is that addition which is done is controlled by quantum mechanics. It's not a classical thing. So that's what helps you in quantum cryptography. And of course, it's all tied up with the same. Okay, sorry.
Regarding locality component prediction, isn't that sound similar to Heisenberg acidic principle and reverse Rayleigh star?
Why do you think so?
Because I feel that sounds similar to this.
Locality equal tells you that I perform measurement on my system and the measurement outcome. Okay, so the act of measurement on my system would not affect the measurement outcome on a distant system instantaneously. How will you guarantee that? So in experiment theory, it is fine. If we do it in the light cone or something, we can do that. Question is in experiment, how will you guarantee that? So you will have to set up the detectors at 2 labs far apart so that it will guarantee that when detection happens in one lab, it is not going to affect the measurement outcome in that. It has nothing to do with Heisenberg. This is true in classical world also. Okay. And detection loophole, that's again nothing to do with Heisenberg. See, for photons, because they don't interact much, detecting them, so how do we detect photon? That 1 photon, 2 photon, photon comes in a detector, you use a diode, for example, so it will excite lots of electrons, those electrons will again excite even larger class of electrons, and then it's a motion of electron that will produce the charge, the current. So you be taken. Okay, so this is how we know basically this is the photon multiplication. Question is, photons, because they don't interact, detecting them also is very easy. We don't have better efficiency, much efficiency. It has nothing to do with Heisenberg.
A question from Zoom participant is, yeah, is entanglement depends on time.
Okay, so whatever we discussed so far is about underlying space-time is non-relativistic. Okay. If you take a relativistic space-time where position and time, displacement and time, they have same status, where Einstein's theory of relativity holds good. There, even if I prepare a joint system in entangled state, and these two subsystems travel, if there is acceleration in the motion of the subsystem, then the amount of entanglement can get affected, and thereby so basically with respect to time, it can affect the entanglement. So this is in the relativistic scenario. Even in the non-relativistic case, because quantum systems are very, very prone to interaction with this environment. So even if I prepare two photons in polarized entangled state, they will not remain in that entangled state for a longer time. So it will decay. With respect to time, actual world, it will decay.
A couple of questions from YouTube.
Okay.
From Vwani Roychowdhury, is teleportation is same as quantum entanglement?
No. So one can show that, in fact, theoretically one can show that in order to have quantum teleportation, and this is in quotation, quantum means it is not, you are not using just classical reason. Quantum. So if you want to have quantum teleportation, then entanglement is necessary between sender and receiver. But even if entanglement is there, you may not have quantum teleportation. So these two are not synonymous.
Yeah, one more question. Is there a possible that entangled particles are no longer a different particle, but same particle in different space?
Okay, so entanglement is something which is physical in the sense that we can perform measurement on these two particles or modes whatsoever and figure out whether they are entangled or not. And one can identify properties of individual particles by performing measurement. So therefore, it is not true that entanglement means of two particles in their same particle. Well, the question is slightly different when you take system of indistinguishable particles, where you have boson, fermions, etc. Is much more difficult. I'm not going into that detail. So far, we discussed only about distinguishable particles, although photons is not distinguishable. Is that when you take distinguishable particles entanglement of distinguishable particles, then there is, you cannot say that entanglement between two particles is one particle. No.
Yeah, couple of announcements from the organizers. Before you leave, please send your feedback. We have provided the feedback form at the entrance, and please fill up the feedback form and then go to us. This will help us to improve our future program. We also have the form to become the member of Tamil Nadu Science Forum. That's also available. The annual subscription is 30. Those who are interested to become a member of Tamil Nadu Science Forum, please do become a member. And we also play some of our publications, science publications and science magazines. Tulir and Jantar Mantar. You can subscribe the Jantar Mantar. Jantar Mantar is in English and Tulir is in Tamil. So we have two science magazines publishing from the headquarters. Please, those who want to subscribe, you can do that here. So that's the announcement. Okay.
Questions?
Sir, my name is Bhuvan, sir. I am studying in Chennai. My question is, what turbine solving for theory of everything, sir?
What?
Complete solving for theory
Theory of everything.
of everything, sir.
What is it?
Why cannot solve?
Why can't we find the theory of everything now? Why can't we find the theory? That came to be very confusing. But unfortunately, and attempt to other will be too complicated, because the world, the universe is too complicated. So theory of everything, it's only for philosophical or science fiction.
I would say we are not in a position till now to either to deny or accept whether theory of everything will be there or not.
But even that we don't. Okay. Okay. Good.
Hi, my name is Jatin. I'm from IMSC. I had a question that entangled, at what length scale is entanglement gets vanished away? Like there will be a scale, and what could be the reason for it?
Okay. So as I said, even in the case of, your background space-time is non-relativistic, that's what we discussed here. Quantum systems are very much prone, as you know, are very much prone to interaction with each environment. So if you take photons, there will be carriers. The photon polarization will be with some photon, and then the photon may be polarized in degree of freedom or other degree of freedom. Interact. So therefore, because of this, so the lifetime of such systems is very small compared to classical systems. Therefore, whenever you put in entanglement, its lifetime is small. I mean, we want to have entanglement with high lifetime, but this is small. The question is the length scale. So length scale, of course, it depends upon what type of interaction you are having. If you are dealing with photon, this is not a problem. You can have two photons polarized entanglement in long distance. But if you have electrons, it depends upon what physical system you are.
Sir, British, my doubt is that British Pondicherry University. Sir, my doubt is that we know that 2 points are entangled. Okay, let's say the 2 are entangled. We take one particle to one end of the universe and other to another end of the universe. So they're correlated. We do a measurement. Okay, so when you do a measurement, one will affect the other. So doesn't mean that the information passes. Doesn't it violate the relativity?
No.
So that is my
Yes, okay. So the point is that yes, it is true that the instantaneous collapse of state happens on the other system when I do something. But this instantaneous collapse cannot be used to change physical information instantaneously. To change physical information, you will have to take the time, like speed of information, like the speed of light. You cannot do it bigger.
Other questions? Yes.
Yeah.
So, is entanglement done only between particles that have 2 states or and they have multiple?
No. I mean, entanglement, as I said, with photon polarization, the singlet state, as I mentioned. So you can express the singlet state in terms of horizontal vertical polarization. You can express it in terms of some other linear polarization like 45 degree, 135 degree. You can express it in terms of circular, right circular, left circular. So it is up to you. So this is the important thing. That when I do measurement in classical world, I can figure out a finitely many, or which is called granular outcomes. So whether it is head or tail, whether it is up or down, something like that. In quantum system, when I talk about measurement of polarization, it can be horizontal, it can be 45 degree, 135 degree, it can be anything. So you can have continuous outcome by setting up your measurements, which is not possible in classical. So the granularity of measurement is there in classical world, but this continuum of granularity is absent in classical.
I just want to add one more. Well, entanglement, the positions are possible. For momentum.
In principle, possible.
How could we know if 2 particles are entangled regardless state of one particle is left to the I was asking that how could we know if 2 particles are entangled regardless the state of the one particle is reflected on the other? Like, two particles separated, right?
State affecting other is, question is when I can affect some system by probing the system, by performing measurement tasks, okay, or doing some operation, maybe rotation, translation, etc. Unless you probe, the state affecting other system, it doesn't make sense physically. So maybe you have something else in your mind.
Like, I'm asking that, good. That's not. Okay, no, if two particles,
Entanglement.
Okay.
What is the method of entanglement?
Okay, so how do you know two particles, two bodies are entangled? or not? So there are different ways of doing that. One way, I told you, is the violation of Bell inequality. You have two photon polarization, you perform measurement of photon polarization, with horizontal vertical, 135 degree, 45 degree, 135 degree, 45 degree. Look at the Bell inequality, see whether it is violated. If it is violated, you are sure it is entangled.
is there any other means?
There are other things, which is called, detection of entanglement. So many other.
Bell's inequality, is it necessary condition or sufficient condition?
If Bell's inequality is violated, then it is entangled.
If it is not violated,
Can I just add here? See, the Bell's inequality which was obtained here, there are many correlations. When you actually do an experiment and calculate that, if it is more than 2 the value, then it is certainly entangled, depends on how much more. It can go up to 2 times root 2, and that's the maximum entanglement. But if it is less than 2, you cannot say whether it is entangled or not. There are more tests required for that. Again, a large amount of research work is done on how do you measure entanglement? How do I know this entangled state is more than the other entangled? These are factors.
Yeah, we can wind up.
Question to.
How to observe the spins of the entanglement particles?
So you just apply this figure out this.
Here, wind up. 6 o'clock.
okay, last question.
It's kind of a weird question to ask, but what I want to ask is, can two different entangled states be entangled with each other?
Complex entanglement.
So, this is a mathematical question you would ask. It's possible mathematically, if I have, let's say, 3 particles, okay, then I can have say ABC. I can have entangled state between A and B. I can have entangled state between B and C. It is possible. I can may also have entangled between A and C. That is also possible. But there is something called monogamy of entanglement, which says that if I increase the entanglement between A and B, entanglement between A and C will decrease. Okay, something like that.
Okay, thank you very much. We have to wind up now.
What are things for you?
There are a couple of things. You want to give any specific reference or anything? Popular reference?
Okay, so actually there is this book by there are many references. I would say that there are some review articles by Alan Aspect. Okay, YouTube also there, so you can figure out those. Several review articles are there. You can look into it. Alan Aspect is also an experimentalist, but it's a very, very good expositor of theory.
Okay. You want to say something?
No, I just want to show this book.
There is a book which Professor Vwani is recommending, When Quantum Physics Was Reborn, The Age of Entanglement by Louisa Gilder. Okay. You may want to have a look at it. I don't know, many colleges and other places may have. And
Yes, but I could come in.
All of them are aimed at the real It is electrical because we don't effectively one of us to convey to us. I would get to that. Even sometimes. Among the three books are quantum mechanics. And the third book on quantum mechanics is the 14th reality. It exclusively devotes EPR paradigms. Then density party. And surprisingly, it's not a part of study topic. Surprisingly, the author of this are very good at this topic. Allied in the full details. Including the graph. The real book.
Thank you very much. So, we will now wind up. Chemistry with our TNS of PSL main person now doing a lot of work. She will propose the word of TNS.
இன்னும் கொஞ்சம்.
So thank you all for coming here. It was a great, it was enthusiastically, first of all, I've just recently joined Science Forum, so I can say the enthusiasm of the Science Forum people for organizing these lectures is really immense. Thank you, Professor Vwani and Professor Sibasish, both of whom agreed very immediately as soon as we approached them. They agreed so much enthusiasm, and it was such a wonderful thing to do. And we would like to thank all for the hall. We would like to thank National Engineering Library people. It's been it's a very wonderful location for all of us to gather and discuss. Except that they leave your bags outside, so now we have to go collect the bags.
Don't break the back.
Thank you, TRG, for moderating it.
Okay, thank you very much. Now, the certificates for the college students will be available.
Yeah, it's available at the desk.